One of the tutors for this subject with PCSG, and we'll be doing, as you know, this is electrical engineering fifth form, and today what we're going to look at is just electricity basics and a little bit of Ohm's law. Nothing too deep, but we're going to go very basic today. So the goals for this class is to understand what current, voltage, resistance is, what current, voltage, and resistance is, and how they relate to each other. And we want to also understand what is Ohm's law and how to use it. So, Rogers, confirm for me that you're hearing me clearly.
Yes.
Okay. So, we're going to interact a little bit through here. Okay, so first thing we have is a conductor. And it's already here. So a conductor is a type of material or element which allows current to flow through it. A good conductor only has one valence electron. Now, you may ask, what does this mean? Now, the first part is pretty self-explanatory. It's the type of material or element which allows current to flow through it. We'll go through what is current a little bit later. So, let me just say it allows energy, or for lack of better words, let's use something like a I don't know, a strainer or something like that there. A good conductor is something that would I use a strainer that has like very wide holes. So let's say that let's say that let me say we're strainer going up with just the path or the residue from what you've done from blending it. Let's say that's the current, and it's flowing through a strainer, and the strainer is either a conductor or something else that we'll get to a little bit after this here. So if the strainer is a good conductor, it means it has large holes, which means that it allows for the path or whatever it is to strain through very easily, to go through very easily without any restriction. It basically allows it to move freely. So that's why I'm going to get onto a good conductor only has one valence electron. Now what that means, I'm not sure how much of you would have done some sort of chemistry or understand how the atom is made up. But the atom is made up of a nucleus and protons, electrons, and how it works is that each the atom has shells, and each shells would contain electrons or something called holes, and holes will be positively charged and electrons are negatively charged. So how it works is that the outer shell, which is called the valence shell, has something called valence electrons, which are the shells on the most outer part of it. I'm sorry I don't have a diagram here to explain it, but I think you guys understand what I'm saying. It has a outer shell, which is called the valence shell, and it only has, and for the material or the element to be a good conductor, its chemical makeup must only have, or it tends to only have one valence electron or one electron on the outer shell. What that does is it allows for other negatively charged electrons or positively charged other negatively charged electrons to move through the atom, because as I said, there's something called holes, and if there's only one negatively charged electron, then there's a whole set of other holes around it which are positively charged, so that allows it conducts, so it would draw, or it would attract the current to pass through it and through the holes and it would pull it towards it. So it allows for the electrons to flow more freely in the allows the electrons to flow more freely and the current to flow freely through the material, and that's basically how you understand what a good conductor is. Just give me a second, please. Right, sorry about that. So we're gonna move on to insulators. So on the opposite end, an insulator is a material or element that stops or significantly limits the flow of current through it. Good insulators have their valence shells full. As I was saying, the valence shells, when it only have one electron, it is a good conductor. When it's full, it is a good insulator. So the conductor is the opposite of an insulator, and the insulator is the opposite of a conductor, whereas the conductor allows for free flowing current and the insulators restrict the flow of that said current. So that being said, we're going to move on to an example of a conductor and insulator. This is just a basic diagram. Insulator, you can see here, is a plastic sheath or plastic tubing, as you would want to call it. These the white, green, and black, those can also be considered as insulators. And depending on the type of material and the thickness of it, it can determine if it insulates better or if it's leaning more towards a conductor. And you can see here, a conductor is a copper wire. You can also have like silver and aluminum, I believe, that are also good conductors. So we for sure have copper, and there are a lot of other elements, but you normally see a lot of copper in wiring and electrical circuits. You will see a lot of wires being mainly based off of copper, and it's not very expensive, so manufacturing it is not that big of an issue. It is fairly affordable, and it does the job pretty well, as it is a good conductor. It allows for current to flow through it well. So now there's something called semiconductors. Now these materials fall into the middle ground, where there's neither a good insulator or a good conductor, right? So it neither insulates things well, neither does it conduct the things very well, whereas it's just flowing very freely, neither does it restrict it very much. These semiconductors are something that we will get a little bit deeper into as we go along in the course, as we start to get to transistors and PN junction semi diodes and stuff like that. When we get to diodes and all that, we will get more into what kind of semiconductors are, where do you see semiconductors and how they're used. So now we get on to what exactly is flowing through or being restricted by these conductors and insulators. So current, something you hear a lot. You also hear like your grandparents say, well, you don't turn off and let your raising that you're wasting current. Well, you don't shut the fridge, you're wasting current, stuff like that. It's me, you always hear about. A lot of people I don't think a lot of people actually understand what current is. So to define current, it is the flow of electrical charge or the flow of electrons, and it is represented, it is the flow of electrical charge and the flow of electrons through a circuit, body, through anything basically. But just make sure you understand that it's the flow of electrical charge. That's the main point. It is defined as the flow of electrical charge, or as I said before, where I was referring to electrons in atoms and stuff like that. You have current is defined as the flow of charge and the flow of electrons, right? So current is represented by the symbol I and measured in amperes, which is also represented by A. Now do not get confused by the symbol and the, I get confused by the symbol and the measurement, right? The symbol I. So if you're looking at a circuit, and we get there a little bit later, once we get there, when you're looking at a circuit, you normally see like this labeling of letters, right? And what you see labeled on the circuit is the representation of that specific unit, right? So current can be considered a unit can be considered a volume. It's not value, but I say unit. I'm not saying unit of measurement, but I say unit, right? So then amperes will be considered a unit of measurement. It's measured in amps, right? So you will get 1 amp, 2 amps, 3 amps, and that's just how current is measured. That's the unit of measurement, amps or amperes. And that is represented by E. So if you're writing down an answer for a question I ask you to solve to find the total amount of current, you can write something and it shows on the diagram the total amount of current, IT, and it has like a 5 amps next to it. The I is indicating that the current and that it is current, and the 5 amps is indicating that's the measurement of the current through there, that there is 5 amps currently flowing through the circuit. That's what we're going to move on to. Now, there are 2 types of current flow. Conventional current flow, right, which is travels from positive to negative. You hear a lot of things saying when you deal with magnets and stuff like that, you go from positive to negative, positive, opposite attract. And you have electron flow. And electron flow goes the opposite direction. Now, relatively speaking, the flow of electrons actually go negative to positive, right? But how it is used in electrical and electronic engineering is really shown or is illustrated going positive to negative instead of negative to positive. So there are 2 types of current flow, which is conventional current, which is positive to negative, and direction and electron flow, which is the direction the electrons actually flow in the circuit. So that's something you just need to know and know for yourself. There are 2 types of things. It may come a little later down, maybe it may not be that major, but it's something to know well, because it can always come later down in your career of doing the electrical or electronic engineering. So let's move on. So we have voltage, right? Voltage is defined as the force that causes current to flow, or it can be seen as the rate at which current flows, right? So voltage, so let me say we have man A that is sitting on a sled, right? Man A is the current. Say use A, right? And then we have man V, right? Because we'll get on a little bit more, you understand why I use V. I think that you should know that by now. But then we have man V that is pushing man A on the sled. So, and man A is carrying, let's say, 5 rolls of toilet paper, right? And we can use those, and we can say those toilet papers are 5 amps, right? And man V, what he's doing, he's the person. So man A is holding these 5 amps. Man V is actually moving these 5 amps from one point to the next, whether it be through a circuit or just from, as I said, one point to the next. Most of the time it is sent through a circuit. If not, the circuit is not complete and you don't have a continuous flow of current or voltage. Okay, so that's the explanation of how those 2 work together. So now we have voltage. Voltage is also called electromotive force or potential difference, and it's represented by the symbol E. Now, as you can see, as you would have seen, let me go back to the previous slide. As you will see, we have a positive side and negative side to a battery. So there's voltage here, right? Now what happens here is there's an electromotive force between the negative and positive side. As you would see in physics with magnets, there's a force electromagnetic force, right? Or electromotive force in the case of voltage, but it creates a force. The flow of voltage will create a force because the negative side will somewhat attract, the negative side and positive side will attract, and it will create a force around them. But how it will flow is it will flow to the right and go all the way around, right? So that's why we have it called electromotive force, right? Or it can also be called a potential difference, because if you look at it this way, you got a negative and positive. So look at it as that you have this difference between them, because you know they're two different things. They're literally a potential difference between them. I think that's the simplest way I can explain that, right? And it is represented by the symbol E. But note well, however, volts is really measured. The voltage is measured in volts, or the common representation of voltage is volts, right? You can see some people using E in circuits, but realistically speaking, the value for it, the value or the measurement or the unit of measurement used to measure voltage is volts. You will see people represent it with the same V, but remember that so say for example, the same way I had I equals to 5 amps, you can have E equals to 5 volts or V equals to 5 volts. So remember that the measurement, the unit of measurement will always be volts, but it can also be represented by the same volts with the same V. Okay, so now we're gonna move on to the last thing in this trio, resistance. So resistance is known as, or defined, sorry, my apologies. Resistance is known as or defined as the opposition or restriction of current flow in a circuit, right? These are resistors. So now the first thing we have is resistance. It is known as or defined as the opposition of resistance or restriction of current flow in a circuit. So what do you think a resistor is? So obviously if you have resistance and then you have something saying resistor, it kind of sounds like, you know, the device that carries out the function of adding resistance to an electrical circuit, right? So as I said here, resistors are devices which carry out the function of adding resistance to an electrical circuit. The symbol of resistance is R. So you will see R in a circuit, you will see R1, R2, and then you will see it's measured in ohms. So you can see R1 is equal to 10 ohms. That is just how the resistance is, you know, represented with R as the actual, let me say, unit, or let's say representation, or just representation, and then ohms is the unit of measurement. Okay, so now next thing we can move on to resistor color codes. Now when you start to build circuits in person, you will have to understand resistors and how they are color coded. You will see they have these bands of colors around them, and what it means, and each of the bands colors have like a specific let's say unit attached to it. So this table here basically explains or shows how the bands are used and expressed, right? And what exactly do they mean, right? So we have a situation where we have this color code. I cannot remember the acronym right now, not one that is you know, appropriate for this class or recording. We have black, brown, red, orange, yellow, green, blue, violet, gray, white, gold, and silver. Now I want you all to focus on black to white, because gold and silver only deal with the tolerances, and we will get to that a little bit later, but we'll get to that as we continue. But we'll start here by just understanding how to find out the unit or the the quantity or the unit of measurement, or how much resistance is in per resistor based on the color code, right? So how we gonna do this is, if you look at the first one, I'm gonna start with the bands. So there normally you have 4 band resistors, 5 band resistors, 6 band resistors, etc., right? So how it's gonna work is that you are going to have, so the first band will be in the for the first band, the multiplier will be 1 ohm, right? The second band, the multiplier would be sorry, my apologies. So for black, so how it works, so the first thing you have, the first band gives you the first number, second band gives you the second number, and the fourth band, which is, so, well, you can have, in the case of a 4-band code, you have the first 2 bands which will give you the numbers, right? The first number and the second number. The third band then gives you the multiplier. So let's look at this for example, right? For the 4 band, we have green, so that means 5. So the first number is 5, right? Second band is blue, so we have 6, right? Then we have yellow, which is a 10K ohm multiplier, right? So you multiply 56 by 10K, you get 560 kilo ohms. And we go over that again. So look at it as in place values. You have 5 in the tens and 6 in the ones, and then you have this multiplier of 10,000. So then you're going to push you all the way up to the hundreds of thousands column, and you're going to have 560,000 kilo ohms. I will literally just have 56 and multiply it by whatever the multiplier is. When you get down to the 5 band, when you get down to the 5 band resistor, the first 3 bands will determine the color, the numbers. So we have red, which is 2, 3, which is orange, and the purple, which is 7. So then we have 237 here. And we have the 4th band now, which is going to be the multiplier. So since the 4th band is black, the multiplier is going to be 1. So you're going to multiply 237 by 1, which will give you about 237. So then this resistor here is 237 ohms. This resistor here is 560 kilo ohms. Now, note well that regardless, it doesn't matter if you have more bands or less bands. The importance is the color of the bands and the order in which they are, which will tell you the value of the resistor. Now it's very important to know that when you are dealing with these resistors in like person, you need to still make sure and go back and measure them to make sure that you would have calculated properly, and also that you did not read the band from the wrong direction. Now, I left out 1 band in both of these. This 4th band in the 4-band code, and this 5th band in the 5-band code. Now, these final bands have something to do with tolerance, right? And from math, you'll see a lot of plus or minus in quadratic equations. When you're dealing with quadratics, you find to see that you're finding the 2 values of x, or when you're dealing with simultaneous equations, anything like that, you're trying to find the values of x, right? And you have a plus or minus. Now, the tolerance means that obviously in every resistor or everything made, it will not be perfect. So what this tolerance does is that the tolerance allows you to gauge what may be the difference, whether it be 1% difference from the actual value of measure. So you have 560K, it could either vary 1% down from that or 1% up from that. This here, its tolerance is gold. The band is gold, so it's plus or minus 5%, right? So we have plus 5 plus or minus 5% of 560. That's where you can see it here, right? Then where the 5 barcode, this one here is brown. So we have plus or minus 1% of the 237, right? Now, this here, as I said, the resistors are not perfect, so this will be included by the manufacturers to give you a gauge of what value may measure based on what value is calculated, how much it will be off. Because as I said, when you're in real life situations and you want to measure the value of a resistor, you have to make sure, and your calculated value of a resistor, also double check and make sure that you measure the same value, because what can happen is that, as I said, the manufacturer is not perfect, so there may be a slight drop in, a lot of the time it's a drop, not necessarily increasing. All my years of dealing with electrical, I've never seen an increase on a resistor that is, let me say, a 1k ohm. I've never seen it like 1.0k ohms or 1.02k ohms. I've never really seen that. I've always seen 999 ohms or 0.9k ohms, 0.9, something like that there. With just a small, what is called margin of error. It's a very small margin of error, but that is what the tolerance is used for. Brown is plus or minus 1%, red is plus or minus 2%, green is plus or minus 0.5%, etc., 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 etc. And as it goes on more, there's less and less of an actual, margin of error, right? So that is why this is here, so that when you have calculated resistors based on the color code, and then you go back to measure to check it, you're understanding. And this is what you should normally remember without having to read all 5 or 4 bands, that there will always be a measure of error or a small margin of error. You need to always remember that there will be a margin of error in whatever you do, because it will never be perfect, and that's just the fact. So whenever you see something that's close to the resistor, a set resistor value that you know exists, so for example, you get a resistor that's supposed to be 1k, and you see it and you measure it and you get 998 or 990 ohms, just know that it is a small margin of error, and it's not going to be the make or break of your circuit, right? Good. So now we've covered the resistor color code. It's something you need to know, because as we go along, this is something that I may probably bring up in an exercise, or like maybe a test that we may have, anything like that, right? So illustration, this is a nice illustration, a simple illustration of voltage, resistance, and current, the relationship between it. Again, so we got here man A, man amp, right? We got man amp right here, map, right? He is he's carrying, let me say, a load inside his stomach or whatever, as in he's carrying food inside his stomach, and the voltage here is moving him because he would have wanted some help because he was too far to move, right? So the voltage was pushing him. So you can see ohm, or the resistance right here, is literally tying him off and making it harder for the voltage to push, right? So this relationship, whereas the amp is what is carrying the substance, or the substance is what's actually containing it, and the voltage is what's moving it or pushing it or carrying that from point A to point B. That's what the voltage is. While the resistance only goal is to slow down how fast the amps move, how fast the current moves, or how fast the voltage pushes it. Now keep note of this here, because it will come into the relationship. This will come into the relationship when you start dealing with Ohm's law, which we're going to head to right now. So Ohm's law. Say Little meme there for you guys. Right. So Ohm's law states that the current flowing through a circuit is let's start over. Ohm's law states that the current flowing through a circuit is directly proportional to the applied voltage and inversely proportional to the total resistance of the current of the voltage, resistance of the circuit. So my bad. Right. So let's take a look right here at this formula in the middle. So it says the current flowing through the circuit is directly proportional to the applied voltage. So this I, as you say, I equals or directly proportional to V. That always means, technically, I directly proportional to V means I equals to V on 1, right? Now, that's what directly proportional means, right? Now, inversely proportional means that I is equal to 1 on R. Or you can write it that, if you write this here into two separate, you can write this here into two separate statements where you have I, an infinity sign, which means proportional in physics, or it can really mean proportional, or I is proportional. Yeah, if you have I and the infinity sign to V, that means I is directly proportional to V. And you have I infinity sign 1 on R, it means I is inversely proportional to R. Now that is important to note because, and this is splitting down, and when you see two of those, we can then write I equals to V on R, right? So this here is very important to note, right? I equals to V on R, V equals to I on R, and R equals to V on I. These three equations are very important to note. This will build the foundation for your whole experience in electronic engineering. Everything you do will have voltage, current, and resistance, whether it's dealing with power, wattage, whether it's dealing with wattage, which is power, capacitors, inductors, anything it would be that you would do in electrical circuits. Voltage, Ohm's law is the building block for every single thing. This here, don't forget this. Whatever we do, V equals to IR. If anything, me personally, I've always been able to remember V equals to IR. That is very easy to remember. I remember the triangle where V is always on top and I and R is on the bottom. So if you want to find I, you have V on R. If you want to find R, you have V on I. And it's right here. So you have I, V on R, V on I. And if you want V, is I by R. It's going across. So that's multiply, that's divide up there. Good. So this here is very important. And we're coming on to the closing of this lesson for today. It wasn't meant to be too long, just going through the basics of electricity and Ohm's law. So now we're going to look at a simple circuit explaining or showing an example of how to use Ohm's law. Next class we are going to go in deeper on how we're going to go in deeper on the types of circuits you would find, types of resistor circuits or types of circuits with loads in them. And we're going into depth with all of that by next week and our next class. Good. So this is a simple example. So this here is asking us find the current in this circuit, right? So we have to remember what we looked at. So we can go back. So the first thing I want you to do is write down, to find the current, remember what current means is current is represented by I. So we have to find I. You can see literally right here, it says to find the current, I equals to V on R. So the first thing I want you to do is write that down. Write down. Next thing I want you to do is look at this circuit and say, what values do we have? We have I equals to V on R, right? We have I equals to V on R. Put that somewhere, write it down. And then write down I equals to something. Since you don't have I equals to anything, just put I equals to question mark. R equals to something and V equals to whatever it is. Now in this case, I'll give you you can pause the video and take 5 minutes to look through that. You may know how to add resistors already in series. If you don't do that, you can do the whole question, and then when we're done going through it, you can look back at it. But I'll give you a second to pause the video and I'll give you a second to try it on your own. Alright, so let's continue. So we have established I, we don't know what I is. So we now want to find out what R is. Now this resistor Now this may not be the best circuit, but in this case there are two resistors in this circuit, and when dealing with resistors in series, which is the circuit type we will get to next week, to find out the total resistance in this circuit, you will add the two resistors together. So you add the 20 ohms and the 40 ohms, and you get a total resistance in this circuit of 60 ohms. Now, resistors are also represented in this form factor as that jagged line here. These are what resistors look like in schematic diagrams. I should have shown an explanation of that, but we'll go through all that next week, right? So we have the two of these here. Resistor 1, let's call this resistor 1, we have resistor 2. So we have RT, which will give us 60 ohms, right? And then we have 120 volts here, which is the total supply voltage on this circuit. I put that down as V, right? You put V equals to 120, R equals to 60, or R total equals to 60, and you start to find out I. Remember, I equals to V on R. Remember that. Good. Now, let's look at this. Remember I said IT equals to Vs on RT. That's just to say the I total equals to the voltage source, which is the 120 volts on RT. So then we have Vs equals to 120, right? We have Vs equals to 120. We have R1 equals to 20 ohms. We have R2 equals to 40, and then we still need to find RT. So I would have said it right now a little bit differently, but you know, it's the same concept. RT would equal to R1 plus R2, which is 20 plus 40, which gives you the same 60 ohms. Remember, ohms is also represented by this omega sign, and it represents ohms, right? So then we're going to find IT. So remember that IT is V on RT, or V on R. In this case, is the voltage supply on the resistor total, the total resistance in the circuit. So then we have IT, which is the total current in the circuit, as 120 divided by divided by 60, which will then give us 2 amps, and that is basically your answer right there. And for today, I think we'll leave it at that. And next week we'll go in deeper into resistor, the types of resistor circuits. We go into how to add different types of resistors and different types of circuits, series, parallel, and we also like to calculate the current and voltage across different types of circuits using Kirchhoff's current law, Kirchhoff's voltage law. I'm not sure if you guys have heard of that, but that's what we look to do next week. So I'm looking forward to seeing you guys next week and having another great session with you guys.